Okay, in this chapter, we are going to discuss double integration method to find the deflection of and slope of beams with the different loading conditions and the different supports. The first one is deflection of cantilever with a point load at its free end by double integration methods. Okay, this is the diagram. The W is the load. It is acting at the end of the beam. The deflection will like this. Then moment, when we take moment at x point, the load W into the distance is del minus x. The bending moment at any section is given by EI into d square y by 2 square. Double differentiate the equation, we will get the deflection and theta value. The theta will be WL square by 2 times of EI. That is OEN is equal to WL cube divided by 3 times of A. YB is the distance moved by the beam. Second is deflection of a cantilever beam with a point load at the distance from the fixed end. By doubly integrating the equation, we get the YB is WA square divided by 3 times of A plus WA square by 2 times of A into L minus A. Here A is the distance from the fixed end. Then the deflection of the cantilever with a uniformly distributed load, the shown figure represents the deflection. First find out the moment at any point x and double integrate the value to get the deflection. Okay, by solving the equation we get the YB is equal to WL power 4 divided by 8 times of EV negative because the deflection in downward direction. The deflection of a cantilever beam with a uniformly distributed load as a distance A from the fixed end. Okay, convert the uniformly distributed load into point load which is acting the center of the A. So the YB, by integrating the values, WA power 4 divided by 8 times of A plus WA cube by 6 times of A into L minus A. The next one is a deflection of a cantilever with a uniformly distributed load for a distance A from the free end. Okay. In this case, we get the YB is WL power 4 by 8 times of A minus W into L minus A the whole power 4 divided by 8 times of A plus W into L minus A cube divided by 6 times of A into A. Next, deflection of a single supported beam carrying a point load at the center. Okay. When we take the moment at a point x, mx is equal to reaction at A into x. The reaction is the load divided by 2. The moment is equal to EA into d square y by dx square. Okay. After that, by solving the equation, we get WL square divided by 16 times of A. Here, the deflection at A and the slope at A and B will be same because it is simply supported and the load is exactly acting at the center. So, the maximum deflection value is WL cube divided by 48 times of EA. Then the deflection of a simply supported beam with uniformly distributed load is also same. The load is W into L. Okay, the reaction will be W into L divided by 2 for A, the same as for B. So RA is equal to RB is equal to W into L divided by 2. Okay, when we solve this equation, we get slope WL cube divided by 28 EI, the negative. Then the deflection is 5 times of WL power 4 into 384 E. These are the numerical problems using the above conditions for different support cases and the different loads. Thank you.